Every C++ program you will ever write starts with exactly one thing, your source code. You type int x equals 42 semicolon, and you see words, numbers, and symbols. But the computer doesn't see that. It sees a raw stream of characters, a sequence of ones and zeros. Before your code can even begin to make sense, the compiler has to break it down into its absolute fundamental building blocks. Think of it like the DNA of your program. Each tiny piece has a specific, critical role. If one piece is out of place, the entire structure collapses. I want to show you something that tripped me up for 3 days when I was starting out. How the compiler actually interprets your code, character by character, before it even thinks about what your program means. Understanding this low-level view is crucial for debugging those cryptic compiler errors. Today, we're going to pull back the curtain on how C++ actually works at this fundamental level. This isn't just about memorizing rules. It's about understanding the underlying mechanisms. You'll learn to distinguish between the 5 core C++ tokens: keywords, identifiers, literals, operators, and punctuators. These are the atomic units of your code. We'll clarify the difference between an expression, which computes a value, and a statement, which performs an action. This includes the critical Lvalue and Rvalue concepts, which become vital for advanced C++ features. You'll understand declarations versus definitions, and how the one definition rule keeps multi-file projects sane and prevents linker errors that can cost you hours. This is the part most tutorials skip. Finally, we'll trace a basic hello world program, identifying all these elements in action. You'll see how even the simplest C++ code is a rich tapestry of these fundamental concepts. Let's start with the very first thing the compiler does: tokenization. Imagine your C++ source code as a long, complex sentence. Before you can even begin to understand its grammatical structure or its meaning, you first need to identify each individual word, number, and punctuation mark. In C++, these individual pieces are called tokens. A token is the smallest meaningful unit in your source code that the compiler recognizes. It's an indivisible building block. The compiler doesn't see I, N, T, space, X, space, equals, space, 4, 2, semicolon. It sees int, X, equals, 42, semicolon. There are 5 main types of tokens. First, keywords. These are reserved words like int, return, or if. They have a fixed, predefined meaning to the compiler, and you cannot use them for any other purpose. Next, identifiers. These are names you choose for entities like variables, functions, or classes, such as myVariable or calculateSum. They must start with a letter or an underscore, and they cannot begin with a digit. Case matters, so myVar and myVar are distinct. Then, literals. These are fixed values directly represented in your code, such as the integer 42, the floating point number 3.14, or the character C. They are the raw data your program operates on. Operators. These are symbols that perform operations, like plus for addition, left shift for output, or logical and for logical and. They tell the compiler to do something with values. And finally, punctuators. These are symbols that organize the code structure, such as the semicolon, parentheses, open parenthesis, close parenthesis, or curly braces, open curly brace, close curly brace. They define boundaries and group-related code. When the compiler first reads your source file, it performs a process called lexical analysis. It takes the raw stream of characters and breaks it down into this sequence of distinct tokens. Think of it like a factory assembly line, where raw materials are sorted into distinct, labeled bins before they can be used. Diagram_ref, lexer_flow. Let's look at a simple line of C++ code and break it down into its tokens. All right, int x equals 42 semicolon. Here, int is a keyword, signaling a built-in type. X is an identifier, the name we chose for our variable. The equals is an operator, specifically the assignment operator. And 42 is an integer literal, the actual value. Finally, the semicolon is a punctuator, marking the end of the statement. Each of these 5 distinct pieces is a token. The compiler sees these individual tokens, not the raw characters, as it moves to the next stage of compilation. A common mistake I see juniors make is trying to use a keyword as an identifier. For example, if you try to declare a variable named int like this, int equals 5 semicolon. The compiler will immediately flag this. You'll get an error message similar to error : expected unqualified -id before int. It's telling you that int is a reserved word, and you can't use it to name your own entities. The token int has a fixed meaning, and you can't redefine it. Now that you understand tokens, expressions and statements are going to make perfect sense. Think of it this way. An expression is like a phrase in English that evaluates to a value. 5 plus 3 is a phrase, and it evaluates to 8. A statement, on the other hand, is a complete instruction, like a full sentence. Assign the result of 5 plus 3 to x. That's a complete action. It tells the program to do something. Formally, an expression computes a value. It can be a literal like 42, a variable x, or a combination with operators and function calls, like x times y plus get val open parenthesis close parenthesis. Every expression has a type, and it might have side effects, like changing the value of a variable. A statement performs an action. Most statements in C++ end with a semicolon. An expression followed by a semicolon, like x equals 5 plus 3 semicolon, becomes an expression statement. Other statements include declarations, control flow constructs like if or for, and jump statements like return. Here is where it gets interesting, and a concept that trips up many beginners: Lvalues and Rvalues. An Lvalue refers to an object that has an identifiable memory address and persists beyond the current expression. Think of x in x equals 42 semicolon. X is an Lvalue. It has a fixed location in memory. An Rvalue, conversely, is a temporary value or a literal that does not persist beyond the expression it's created in. In x equals 42 semicolon, 42 is an Rvalue. The result of 5 plus 3 is also an Rvalue. You can assign an Rvalue to an Lvalue, but you cannot assign to an Rvalue. You can't write 42 equals x semicolon, because 42 doesn't have a persistent memory location to store x. Let's write some code to illustrate this. I'll declare an integer I and set it to 10 and another b to 20. Then I'll write int result equals a plus b semicolon. In a plus b, a is an Lvalue, b is an Lvalue, and a plus b is an expression that evaluates to an Rvalue, the temporary sum 30. This temporary 30 is then assigned to result, which is an Lvalue. The entire line, int result equals a plus b semicolon, ending with a semicolon, is a declaration statement. If I then write a equals 5 semicolon, that is an expression statement. 5 is an Rvalue, a is an Lvalue. The assignment operator equals itself evaluates to an Lvalue reference to a, which is a nuance we'll cover later when we talk about operator overloading. The most common mistake with statements: forgetting the semicolon. If you write int x equals 42 without the semicolon, the compiler will try to parse the next line as part of the current one, leading to confusing errors. You'll often see something like error : expected semicolon after expression. It's a simple fix, but it can be frustrating when you're starting out, because the error might appear on a line after the actual mistake, making it seem like the next line is the problem. You've heard me use declaration and definition already. The intuition is simple. A declaration tells the compiler, hey, a thing with this name and type exists somewhere. It's like a promise or a forward reference. A definition, however, is the actual creation of that thing. It says, here it is, fully formed, taking up memory, ready to be used. It allocates storage and provides the full implementation. For example, extern int y semicolon is a declaration. It tells the compiler that y is an integer defined elsewhere, perhaps in another source file. The compiler knows its type and name, so it can compile code that uses y. But y doesn't exist in memory yet in this specific translation unit. Conversely, int x equals 42 semicolon is both a declaration and a definition. It declares x as an integer and immediately allocates memory for it, initializing it to 42. Most variable declarations you write are also definitions. This distinction is critical because of the one definition rule, or ODR. The ODR states that in a C++ program, every variable, function, class, or other entity must have exactly one definition. Not 0, not 2, but 1. This is enforced during the linking phase. You can have multiple declarations of the same entity across different source files or even within the same file, as long as they are consistent, but only one definition. This rule prevents ambiguity and ensures your program links correctly, avoiding those dreaded multiple definition linker errors. Diagram_ref, Adra_concept. Let's consider two files. In my_header.h, I might declare a function. Void my function open parenthesis, close parenthesis, semicolon. This is a declaration, a promise that my function exists. Then, in my_source.cpp, I would provide the definition. Void my function open parenthesis, close parenthesis, open curly brace, standard cout left shift, quote hello from function, quote semicolon, close curly brace. This is the single definition, the actual implementation of the function. If another source file, main.cpp, includes my_header.h, and then calls my function open parenthesis close parenthesis, everything works. The compiler sees the declaration in main.cpp, and the linker finds the single definition in my_source.cpp. This separation of declaration and definition is fundamental to C++ project structure. The most common OD or violation happens when you define a non-inline function or a non-const global variable directly in a header file. If my function's body was in my_header.h, and both my_source.cpp and main.cpp included it, you'd get two definitions. When you try to link those two compiled object files, the linker would complain, error: multiple definition of my function. This is a classic C++ error that tells you exactly what happened. You broke the one definition rule. Now that you understand tokens, expressions, statements, declarations, and definitions, let's put it all together in the simplest C++ program. Hello, world. Every C++ program begins execution in a function called main. This is the entry point called by the C++ runtime. I'm going to write the classic hello, world program. It looks like this. Let's walk through it line by line, identifying all the elements we just discussed. The first line, #include less than IOStream greater than, is a preprocessor directive. It tells the compiler to literally copy the contents of the IOStream header file into this source file. This header provides declarations for input and output stream objects, like standard cout. Next, int main open parenthesis close parenthesis open curly brace. Close curly brace defines our main function. Int is a keyword, the return type. Main is an identifier, the special name for the program's entry point. The parentheses, open parenthesis, close parenthesis, are punctuators for the function's parameter list, which is empty here. The curly braces, open curly brace, close curly brace, are punctuators defining a compound statement, the function's body. Inside main, standard cout left shift, hello world, left shift standard end L semicolon, is an expression statement. Standard cout is an L value, the standard output stream object. The left shift is an operator, the stream insertion operator. Hello, world, is a string literal, an R value. Standard end L is another L value, a manipulator that inserts a new line and flushes the output buffer. Finally, return 0 semicolon is a jump statement. Return is a keyword. 0 is an integer literal, an R value. It indicates successful execution to the operating system. The semicolon is, of course, a punctuator, ending the statement. When you compile this with a command like g++ hello.cpp-o hello, and then run it with /hello, you get exactly this on screen. Hello world. So what have you learned today? First, you now understand that your C++ code is first broken down into fundamental tokens, keywords, identifiers, literals, operators, and punctuators. This is the compiler's first step in understanding your program. Second, you can now distinguish between expressions, which compute values and can be L values or Rvalues, and statements, which perform actions. This distinction is crucial for writing correct and efficient C++. And third, you understand the difference between declarations and definitions, and how the one definition rule prevents linker errors in larger projects. This knowledge will save you countless hours of debugging down the line. Next time, we get our hands dirty with the actual building blocks of every program: basic input, output, and comments. We'll dive deeper into how to get data into and out of your programs, and how to make your code readable.